What's up, AP Physics, C, Electricity and Magnetism student? Welcome back to our Elegant Physics videos. Today's topic 11.6 and 11.7, Kirchhoff's loop rule, Kirchhoff's junction rule. So let's jump right in. Kirchhoff's junction rule, or the KJR. So far we have only seen single source circuit. To solve circuit with multiple sources, we will need new tools. Now remember that current changes only if the wire splits into two or more. Points where a wire splits are called junctions or nodes. Kirchhoff junction rule, the KJR, the sum of currents entering any junction must equal the sum of currents leaving that junction. Mathematically, can be represented by the sum of In is equal to the sum of I out at a given junction. The junction rule is just a statement of the conservation of electric charge, which means the total amount of charge entering and exiting a junction per unit of time must be equal. Whatever current enters a given point in a circuit must leave that point because the charge cannot build up or disappear at a point. So for example here, this point is known as node or junction. Now let's assume that I1 is entering the junction as well as I2 and I3. Only I4 is leaving the junction. Applying Kirchhoff's junction rule, we can write the In are I1, I2, and I3, the I out only I4, or we can rewrite it in this way. I1 plus I2 plus I3 minus I4 is equal to 0. Now here in the last equation, this represents a linear equation. By solving this linear equation, we can easily find the missing current. So exercise 1, the figure shows a circuit composed of a battery and the three identical resistors. Which of the following correctly relates the current I1, I2, and I3 in the resistors to the current I battery in the battery, and provides reasoning that support the stated relation. Let me remind you that the total amount of charge according to the conservation of charge for entering and exiting a junction per unit of time must be equal. In other words, the current entering and exiting a junction must be equal. Now here, the battery sent current I. This current at the junction point will split it into three currents. As you can see here, this current, the current I battery, will be entering the junction. I1 and I2 and I3 are leaving the junction. By applying the Kirchhoff's junction rule, we can write that summation of In equals to summation of I out. Now In, it's only the I battery, and I out are I1 plus I2 plus I3. And the correct answer is A. But why A? Because the total amount of charge entering and exiting a junction, this is the conservation of charge statement per unit time. This is the current actually must be equal. Now next, exercise 2. A junction in a circuit consists of three wires connected together. Which of the following diagrams could indicate the direction and the magnitude of the current in the three wires? Now, again, here we need to apply Kirchhoff's junction rule in the given three cases. Uh, so let's start with the first one. We know that Kirchhoff's junction rule said that the summation of In should be equal or must be equal to the summation of I out. Now here we have only one in, which is equal to 2, but this does not equal to the out, because out 3 and 5, which means this it's going to be 8, and it's not equal to 2, so it's not A. Now what about the second case? We have only one current entering the junction, which is a 3 ampere, and two currents are leaving the junction, so they are not equal, then not B. What about C? We have three currents leaving the junction, and no current is entering, so it's not C again. Now what about D? Now definitely D will be the correct answer because we have two currents entering the junction, 2 and 3, and this is exactly equal to the current that is leaving the junction. It's equal to 5, so the correct answer would be D. The figure shows connected wires in a portion of circuit. What is the magnitude of the current I? To solve this question in a smooth way, we need to apply a strategy. The strategy is known as the boxing method or the boxing strategy. In this method, we will draw a box to hide the unnecessary part of the circuit. and then we apply the junction rule on this box. So this is useless part. I don't need it in my solution. So we're going to hide it from our calculation. We just need to consider this line, this line, this line, this wire, and that wire. And we will apply the junction rule on this box such that the summation of current that entering this box is equal to the summation of current that leaving this box. Now, the current that are entering this box, actually the 8 amps, the 7 amps, and let's assume that the current I is entering the box. So we can choose the opposite way. It won't affect the result. However, the final answer, it may be negative, but here, since we are looking for the magnitude, the minus sign is just an indication that we have to choose the wrong direction, and the proper direction will be the opposite way. Now, I will use I as current that entering the junction. Now, the current that are leaving the junction or the box are the 1 amps and the 2 amps. Now, we just calculate 8 plus 7 is 15, equals 1 plus 2 is a 3. Now, moving 15 to the other hand side, I equals 3 minus 15, and the final answer is minus 12. We got minus sign, which means we have uh, assumed the wrong direction for the current. The current should be in the opposite way. So never mind, because we are looking for the magnitude, and the minus sign just tell us that the direction is in the opposite way. But the numerical value is the same, whether we choose it correctly or in the wrong way. The numerical value is 12 amps, and this is the magnitude of the current, which means the correct answer is C. The figure shows a portion of an electric current. The 4 ammeters indicate the magnitude but not the direction of the current at different locations. What is the magnitude of the current I in the middle horizontal segment of the wire? Okay, so here let's pause and think strategically. A very important detail in this question is that the ammeter shows only the magnitude of the current uh, and not the direction. That means we should not guess the direction right now. We don't do that in this case. Instead, we should look for a value of the middle current that can make sense at both junction, because here we have 2 junctions. Now let's examine the left junction first. So we're going to focus on the left-hand side. We see a current of 3 amps in the horizontal branch and 4 amps in the vertical branch. Since the directions are unknown, there are 2 possibilities. Either these currents are combining, which would make the middle current 7 amps, so 3 plus 4 is equal to 7. This is the first possibility. And the second possibility, the current is entering, one of the current is entering while the other is leaving. So for example, 3 is entering and 4 is leaving, which means it's minus 4 because it's leaving, and they are making up I. Let me explain this with more details. We know that, let's assume this is leaving. So we have this one is entering and this one is leaving as well. So 3 is in and 4 and I are leaving. So out. This is out, this is in. Now moving 4 to the other hand side, 3 minus 4 is equal I. So I is equal minus 1, for example. But pay attention here, we are looking for the magnitude. So even if I swap between which current is leaving or entering the junction, the result will be the same, and it will show the numerical value 1. So even if I swap, such as 4 minus 3, the answer will maintain 1. The magnitude is the same. So don't worry about the direction, the chosen direction here, or which one is leaving or entering the junction, because here we are interested in finding the magnitude. So again, the possibilities in the first junction are the first one, 7 amps, if both of them are entering the junction. And for the second possibility, one of them is entering. Let's assume that 3 is entering and 4 is leaving. So the answer is minus 1 amps. But since we are looking for the magnitude, it will be 1 amp. Now let's move to the right junction. Here we have 3 amps in the horizontal branch and 2 amps in the vertical branch. Again, because the directions are not given, there are 2 possibilities. If currents combine, the middle current would be 5 amps. So if 2 and 3 are combining, then, or are combined, then 2 plus 3. So this is the second junction. The two possibilities are 5 amps, and the second possibility, if one of them is entering, the other one is leaving. So let's say 2 minus 3, the answer is minus 1, but since we are looking for the magnitude, so the answer is 1 amps. Even if I swap between the directions, 3 minus 2, we are interested in the magnitude, so it will give us the same magnitude again. So from the right junction, the middle current could be 5 amps or 1 amp. Now, here is the key idea. The correlate current in the middle must satisfy both junctions at the same time. Now, from the left side, the options are 7 or 1. The right side, the options are 5 or 1. The only value that appears in both sides is 1 amps. Therefore, the magnitude of the current in the middle horizontal segment, it should be 1 amp. Again, we don't care about the direction of this 1 amp, we just need the value, and the correct answer should be A. The diagram shows portions of 3 different circuits with currents in some of the circuits branches indicated. Which of the following correctly compares the currents Ix, Iy, and Iz? So once again, here we will apply the boxing strategy or boxing method to solve this complicated problem. Actually, we don't really care about what's going on in the 4 resistors. So let's use the box to hide them. But before I hide them, I need to know what is the current here. Now, according to Kirchhoff's junction rule, we have 2 currents are leaving the junction and only 1 current here that entering, because both of them are leaving, then this one should be entering in order to balance the situation. And it should be equal to 7 amps because always the current that is leaving is equal to the current that entering. So let me write here that the current is inward and it's 7 amps. Now we use the boxing method to hide this part. I don't need it. Now we apply the junction rule on this box. Now, actually, we have 2 currents are entering the box, the 6 and 2, and from this side, and from that side, we have another current that is entering this box, which is 7. So let me add it here. We have only one box leaving this junction, which is Ix. So Ix is 6 plus 2 plus 7. Then the Ix is equal 15. Let's skip the value here because I will need it in order to complete the ranking. Now, again, before I hide my electric circuit, leaving only this wires free, let me calculate this current here. Now we have one current entering the junction and one current is leaving the junction. In order to balance them, to make them equal, the current here, it should be also leaving the junction with 1 amps. Now they are balanced. So one current entering the junction, 2 currents with the same value. The summation of these 2 currents should be equal to the one that entering the junction. So this is 1 amps. Now we apply the boxing method. We just hide this part, we don't need it. Now we apply the Kirchhoff's junction rule. The summation of current in is equal to the summation of current out. How many currents are entering the box? We have 2 currents, 6 and 2. Only 2 currents are leaving the junction, Iy and 1 amps. Now moving 1 amps to the other hand side, we change the sign to minus 6 plus 2 minus 1 equals Iy. And 6 plus 2 is 8, minus 1 is 7. So Iy is equal 7 amps. Till this moment, Ix is the greatest current. Now we still need to evaluate this electric circuit. Now again, we will need to calculate this current here in this wire. How many currents are entering the junction? Actually, this is a repetitive case. So the current should be the same as the before because 4 amps is entering, 3 amps is leaving. So this current must be 1 amps and it should be leaving the junction. Now we apply the boxing method. We hide these resistors, we don't need them. Now we have actually 2 currents are entering the junction, 2 plus 6, and only 1 current is leaving the junction, or 2 currents are leaving the junction, sorry. They are Iz and 1 amps. So you can notice now that the result will be the same as the previous case. So Iz also will be 7 amps, which means Ix is the greatest current, and then Iz equals to Iy. So Iz and Iy are equal and they are smaller than the Ix. And can be found here. So C is the correct answer. Now, a second important rule in electric circuits is the Kirchhoff's loop rule, the KLR. Kirchhoff's loop rule, the sum of the potential differences across all the elements around any closed loop must be zero. Mathematically, can be represented via the summation of delta V is equal to zero. The junction rule is a statement of conservation of energy. If a single charge makes a complete loop around the circuit, conservation of energy says that the delta potential, electric potential, must be equal to zero. In circuit terms or circuit language, the summation of delta V is equal to zero. So for example, if we have this electric circuit and we choose to circulate the circuit or the closed loop here in clockwise direction, then the delta V here and the delta V here and the delta V here will be added up to zero. Now, this electric circuit consists of 3 loops. The first loop is this one, and the summation of the delta V must be equal to zero as we circulate around this loop. Even for this small loop, the delta V will be equal to zero. And for the third loop, this is the biggest one, this is the closed loop. Now, the way we circulate around the circuit, it can be clockwise or even counterclockwise. We can circulate in this way, and also the summation will be always ends with a zero. Now, how we can calculate the potentials in closed loop, we need to follow this chart. Now, after we choose the circulation, the direction of the loop, if our direction is entering the positive terminal of the battery, then we must use minus the electromotive force. Now, the second case, after we choose our direction for the loop, and we found that we are entering the negative terminal of the battery, then the electromotive force should be written as a plus epsilon or plus electromotive force. For the resistor, if the current is entering the resistor like this, and the direction of the loop or circulation is the same as the direction of the current, then we should write the resistor as minus delta V. And remember, delta V here should be expressed using Ohm's law. And it should be written as minus Ri or minus IR. Now, what if the resistor is leaving the current is leaving the resistor and the loop is in the opposite way? If the direction of the loop and the direction of the current are opposite, then we use plus delta V again using Ohm's law. You can write it as Ri or plus IR. Now let me solve some examples to clarify the technique. The figure shows a circuit where a battery EMF is connected to 2 resistors with identical resistance, knowing that the R is 30 ohm and the electromotive force is 24. So the electromotive force here actually is 24 volts. The R here is 30, and the 2R here, 2 times 30, which means it's 60. Now the thing is, they want us to use Kirchhoff junction rule to calculate the current in the circuit and the voltage across each resistor. So let's start with the first part. However, for the second part, I will use Ohm's law directly. No need to apply Kirchhoff's junction rule. We will apply Kirchhoff junction rule only for the first part. Let me remind you that we have many techniques to solve this problem. To find the current, we simply write I main, the main current in the circuit is equal to the electromotive force or over the R equivalent. It will give us directly the answer. Moreover, for part B, we can use the voltage divider to calculate the potential difference here and the potential difference there. But to serve the new idea, I will use only Kirchhoff's junction or loop rule in order to find the current. First of all, whenever I want to apply Kirchhoff's Kirchhoff's loop rule, we should assign the direction of the current. Now I will choose the direction of the current uh, uh, such that it will be from the positive terminal of the battery to the negative terminal of the battery. And the direction here will be like this. And across from the battery will be like this. and through R 2R, it will be like this. So since we have one current, we will have one direction for the current, and we should stick to this direction. Then we choose the direction for our loop. So we can circulate within the direction of the clockwise or in the counterclockwise direction. Now we apply Kirchhoff's loop rule. Remember that when we apply the Kirchhoff's loop, we should start from a specific point. I will start from here and I will follow the same direction of the loop. So the direction of the loop will be here upward, then to the right, then down, then again to the left, and I will stop once I achieved the starting point again. Now, since the direction of the loop is entering according to the direction of the loop, we are entering the negative terminal of the battery. When we enter the negative terminal of the battery in Kirchhoff's loop rule, we use minus sign for or plus sign for the electromotive force. Now we complete the looping. Now here we can compare the direction of the loop with the direction of the current. If we found them in the same direction, then we're going to use Ohm's law with a negative sign because they have the same direction. So minus R times I. Now for the second resistor, also here the direction of the current and the direction of the circulation is the same. So again, we use the minus Ri. Now we return back to the initial point. So we set equal to 0 because the summation of delta V is equal to 0 according to Kirchhoff's loop rule. So we just write plus electromotive minus delta VR minus delta V of the 2R. And this is the expanded form of the formula. Now we can take R, or we can combine Ri and minus 2Ri, and this will be minus 3Ri. We move the minus 3Ri to the other hand side, it becomes a plus 3Ri. Now remember that we are interested in finding the current, so we move everything else to the other hand side. And it becomes I equals electromotive force over the 3R. After we move 3R to the other hand side, the electromotive force is given by 24. And the 3 times R and the single R is given by 30. And the answer would be 0.27 amps. Now, to find the voltage across each resistor, we just need to apply Ohm's law in each one of these resistors. For the first resistor, Ohm's law states that delta V is equal to R times I. The R is given by 30, and the current is 0.27 or 0.2266, and this will give us delta VR to be equal 8 volts. Now, what about 2R? We apply the Ohm's law on the 2R resistor, and that gives us the delta V2R equals 2Ri, because the resistance here is 2R. I wrote the resistance to be 2R. 2 times 30 times 0.20 or 266, and the answer is 16 volts. Now, notice that if you add 8 to 16, it will give you again the voltage across the source, and the voltage across the source is 24. Now, another example. In circuit above, the EMFs and the resistance have the same values shown. The current I in the circuit is 2 amperes. The resistance R, so we know that the current in the circuit is 2 ampere. Now here, whenever we have more than one source, try immediately to think or to solve the question using the Kirchhoff's laws. And specifically here, I will need to use Kirchhoff's loop rule. Now, to apply Kirchhoff's loop rule, we will need to assign the direction of the current first. So the direction of the current will be this way in all branches or wires. And then we will start from a specific point. Usually, I prefer to start from a point that are located next to the battery, before or after. And then we assign the direction of the looping. So I will use this direction for my loop. So this direction is the clockwise direction. Otherwise, you can use the counterclockwise and the final result will be the same. Now, let's start from this point with rotating with the direction of my loop. So I will rotate now to the right. Now, since I'm entering the negative terminal first, then the electromotive force should be written with a plus sign. So this is a plus 12 actually. Now complete it to the other battery. Notice that in the second battery, we are entering first the positive terminal, which means the sign should be minus the value of the electromotive force, and the value of the electromotive force here is 6 volts. Now, we should stick to the same direction for the current. Now, the current is in this direction, and my loop, my rotation is clockwise, so they have the same direction, which means we should apply Ohm's law with negative signs. So negative, since they have the same direction, my loop and the assigned current. So the resistance multiplied by the current. Now, again, we complete the rotation. Now we have achieved this resistor. The direction of current should be maintained the same, and the direction of current is to the left. My loop is also to the left, the direction of my loop. So they have the same direction, the direction of the loop and the direction of the current. So we should write Ohm's law with the negative sign, so minus Ri. Now also here the direction of the loop and the direction of the current is the same, so minus 1.5 I. Now we complete the looping until we reach the last resistor. The direction of the current should be at the last resistor in this way. So this is exactly the same direction as my rotation. And we should assign the minus sign for this voltage, and minus 0.3, the resistance times the current, or should be equal to 0 according to Kirchhoff's loop rule, because the summation of the voltages should be added up to 0. Now we combine the similar terms. 12 minus 6 is 6. 0.5 minus 0.5 and minus 1.5 is minus 2. So 6 minus 2i minus Ri equals to 0. Now we know that the current is 2 amps. So 6 minus 2 times 2 minus R times 2 equals to 0. Minus 2 times 2 is minus 4. So, or we simply move R times 2 to the other hand side and it becomes plus R times 2 or plus 2R. Now 6 minus 4 is 2, and then R equals 1 ohm. So the correct answer should be A. And the circuit above the EMFs and the resistance have the same value, or in the circuit above, the EMFs and the resistances have the values shown. The current I in the circuit is 2 amps. The potential difference between points X and Y. So we need to find what is the delta V X and Y. We can solve this question using Kirchhoff's loop rule. Remember that Kirchhoff's loop rule states that the summation of delta V around the closed loop, it should be equal to 0. Now, we don't need the whole loop. We just need part of this loop or part of this circuit, and we will use only this half of the circuit to calculate the delta V xy. First of all, we assign the direction for the current. So the current is rotating in this loop in this way, and we choose a direction for our circulation, and the direction of the loop will be in this way. You can use the counterclockwise direction and you will get for sure the same result. The starting point, I will use it from this point. So I will start from here. Notice that if my direction is clockwise, then when I achieve the resistor 0.3 ohm, my direction will be exactly the same as the direction of the current. Using the previous chart, we will know that the sign of the potential for this resistor will be minus. Applying Ohm's law, and this is gonna be minus delta V of the 0.3 ohm. Now we complete our rotation. Now we can notice that we are entering the negative terminal of the battery using our loop direction. And when we enter the negative terminal, we use the electromotive force with the plus sign. Now we complete our rotation. Now we go down. Here we have the delta V xy, which is unknown. So we write it in our equation because this is the potential difference that we need to find. We complete the rotation. Now we are at the resistor 1.5 ohm. Remember to assign the direction of the current. The direction of current in this loop will be the same. Since the direction of my loop and the direction of the current is the same, then we use minus sign for the potential difference across the resistor. Now applying Ohm's law, we will get that the delta V of the 0.3 is 0.3 I, resistance times current, plus 12, plus the delta V xy. Again, this is the resistor. We know that the resistor is the product of current times resistance. So 1.5 is the resistance of this resistor multiplied by the current. Now we combine the like terms, or before we combine the like terms, we substitute the value of the current. So 0.3 times 2, because the current is given by 2 amps, plus 12 plus delta V xy minus 1.5 times 2 equals 0. Now we combine the like terms, such as this one, this one. So 0.3 times 2 is 0.6, 1.5 times 2 is a 3. Now we combine them together, 0.6, 12, and minus the 3, 8.4 plus delta Vxy. We move the 8.4 to the other hand side, and the delta Vxy is minus 8.4 volt, which means the correct value is 8.4 volts. Exercise 6. The figure shows a circuit with the 3 batteries and 3 resistors with the EMF of each battery and the resistance of each resistor indicated. Which of the following equations expresses a correct Kirchhoff's loop for a portion of the circuit? As you can see here, we have 4 choices, so 4 possible solution for a single loop, because each one of these equations represent a loop. Now, since we are talking about loop, the possible loops here are this loop. This is the first loop. This is the second loop. And the last loop will be this one, the large loop. But as you can see, all of these loops contains resistors. So A does not contain any resistance, so it cannot be A. Now, what about the other possible solution? We need to evaluate each one of them independently. Now, as you can see here, E1 is positive, and it contains also, this equation contains negative E2. So let's focus on E1. E1 and E2 are belong to this loop. So we're going to use this loop. E1 is positive, so we will choose the direction of our loop such that the direction give us plus E1. And this can be done if we are rotating clockwise, because when we are rotating clockwise, once we rotate and achieve the battery E1, then we are entering the negative terminal, which means E1 should be written as plus E1. Now let's skip R1 for a while, because if E2 is written with a negative sign, then this must be possible, or this possibly would be the correct answer. So let's find out. When we complete the rotation to E2, we are entering the negative terminal. So E2 should be written as a positive sign, but this is not true for B. B written E1 as a positive, but E2 is negative. So no need to evaluate the rest of the potentials. So also it's not B, not A, not B. Now what about C? C contains E3 and E1, which means we are talking here about which loop? The loop that contains E3 and E1. And I mean by that this big loop. Now what will be the direction of rotation? The direction of rotation, or the loop, should give us minus E3. To give us minus E3, then the direction of the rotation will be clockwise, because we are entering now the positive terminal. So E3 should be written as minus E3. Now we complete the loop to E1. We are entering the negative terminal. So this is plus E1. The first two terms are correct. So let's complete. Now we complete the rotation. As you can notice here, the current and the direction of the loop is the same, which means the potential difference across R1 should be written as minus I1 R1. And this is not exactly the same as in choice C, because it's written with the plus sign. So also C should be suspended. And after we suspend or eliminated all the other choices, we end with D, and the D should be the correct answer. And let me show you that. Okay, now E2 and E3 are included here in this equation, which means the loop that we should consider is a loop that contains E2 and E3, and this is actually the loop. Now the direction of the loop, it should be such that E2 is positive. And to make E2 positive, we should rotate in the counterclockwise direction to enter the negative terminal. Because if we enter the negative terminal, E2 should be written as plus sign, with the plus sign. Now, what about E3? We complete the rotation up to E3. Now, at exactly E3, we are entering the negative terminal again, so it's going to be E3 plus. Now, we complete the rotation. The direction of my loop and the direction of the current is the same. So, R3, the potential difference across R3 should be written as minus I3 R3. Yes, this is a true. The third term is correct and identical to my third term. Now we complete the rotation. Here at R3, the direction of my loop is the same as the direction of the current. So this means that the potential difference across R2 should be written as minus sign, and I2 times R2 and all are equal to 0. This is exactly the same in choice D. The figure shows a portion of a circuit that includes two batteries and two resistors as indicated. Which of the following equations express Kirchhoff's loop rule for the portion of the circuit shown? Now here we have a single circuit or a single loop. And as you can see from the choices that always E1 should be positive. So I will choose my direction of rotation such that I'm entering the negative terminal of my battery in E1. So this is the negative terminal, which means the direction of the loop should be in this way. And this way is the clockwise. Now, when I rotate in a clockwise direction, entering this battery from the negative terminal, so this is a plus E1. Now the direction of my loop, the direction of the current is the same, so this should be written as minus R1 I1. Now we complete the circulation. Now here, the direction of the loop is opposite to the direction of the current, which means the potential difference across R2 should be positive. So plus R2 I2. And finally, we are entering the positive terminal of the battery, which means the electromotive force here should be written as negative sign equals to 0. Reorder the equation again. So E1 minus E2 minus I1 R1 plus R2 or I2 R2 equals to 0. And the correct answer, it should be B. For the circuit diagram shown in the figure, the current I is in the clockwise. So the current, we have only one current in clockwise direction. So the current in this way. This is not the direction of my loop. This is the direction of the current. And we're going to stick to this direction. Which of the following equation expresses the Kirchhoff's loop rule for the circuit? Remember that the Kirchhoff's loop rule states that the delta V summation of delta V around the loop should be always equal to 0. Again, as you can see here, E1 is positive, which means we're going to choose our circulation, the direction of our circulation, such that our loop is entering the negative terminal of E1, and this can be done if we choose the direction in the clockwise. Here we are entering the negative terminal of our battery, so E1 is plus. And we complete the circulation. Now here, the current and the loop have the same direction, which means the potential difference here should be negative. So negative I times R1. Also, here we are entering the negative terminal of E2, which means E2 should be written as plus sign. Here, the direction of the current and the direction of the loop is the same. So the potential difference across R2 is negative. So negative I R2 equals 0. Let's reorder the equation again. Plus epsilon 2. So it should be both plus. So it's not B. It's not D. Now minus I R1 and minus I R2. And the correct answer is C. Now, exercise 9, the figure shows a circuit made from a battery and three identical long, thin cylinders that are made from the same resistive material. Four labeled points at the corners of the circuit are also indicated. Which of the following graphs best represent the electric potential as a function of position? Now, here we need to evaluate the graph that truly shows the variation of the electric potential with respect to the position. So as we circulate around the circuit, how the electric potential uh, would change along the circuit loop. Each graph starts at point A and traverse the circuit clockwise. So the starting point is A, and we are rotating clockwise until we reach A again. So since we have three identical long cylinders, so identical cylinders with the same resistive material, remember that the resistance is given by rho L over A. So identical cylinders with the same resistivity, it means we are dealing with the same resistance here. Since the three resistive cylinders are identical and the circuit is a single loop, the same current passes through each one. That means the electric potential decreases by the same amount across each resistor. We know that when the current passes through a resistor, the electric potential difference will decrease as well as the electric potential energy. Since there is a relationship between electric potential energy and the electric potential difference or the voltage, and it's given by U is equal Q times V. If the V decreases, then the U decreases, and we can decrease the V or the potential difference when the current or the electric charges passes through resistor or any other electrical component except the battery. So on the graph from A to B, from B to C, and from C to D, we should see equal drops in the electric potential. And when I say drop, it means the line goes down. And since they are dropping equally, then the line will be decreasing in continuous way. So these are shown as a straight downward segment. Now then from D to A, instead of having decreasing in the potential, since we are passing through the battery will increase the electric potential, so the graph must rise upward. Now, and because of the conservation of energy, the total rise across the battery must exactly match the total drop across the three resistors. So we started dropping from here, so the battery will rise it to here. And the amount of dropping or decreasing should be exactly equal to the amount of increasing. And this is found here in this graph. So the correct answer is actually this graph. If this is A and this is B, C and D, so the correct answer is B. The figure shows circuit where a battery of EMF E is connected to two resistors with the indicated resistance. And electrons is initially located at point P, so here we have electron, and then moves through one of the resistors. Remember that the charge of the electron is equal to minus E. So it will move through one of the resistors. So we have two possible directions for this electron. It can go in this way or that way. By how much does the electric potential energy of the electron field system change? So here they want me to find by how much the delta U will change as the electron moves through the resistor. Now, first we need to determine in which resistor the electron will move. Now we know that the conventional direction of the current will be from the positive terminal to the negative terminal, and the direction of the electron will be always from the negative terminal to the positive terminal. Now completing the circulation, the electron will complete its motion to the positive terminal from this direction. So actually the electron will pass through the resistor R. Now, since it will pass through the resistor R, the delta U can be written as a Q times delta V. Now, the charge here is the electron, which is minus E, and the potential difference across this resistor. Now, if we decompose this resistor into three resistors, identical resistors, remember that this 2R can be written as R2 resistors in series. Then the electromotive force, it will be divided across the three resistors equally. So how many resistors that we have? We have three resistors. So each one of them will take equal part of the electromotive force, and this equal part will be equal to electromotive over 3. So actually the potential drop across the resistor R will be E over 3. So we substitute here E over 3. Now reordering this equation, and the delta U will be equal to minus 1/3 A multiplied by the electromotive force. So the correct answer is A. When a battery and a resistor are connected together by conducting wires in a single loop circuit, an electric field is generated within the circuit. Which of the following statement is true about the electric potential energy for the system composed of circuits, electric field, and single electron moving through the circuit? Now remember that the electron is always moved from the low potential to high potential. So if we are assuming that this is the battery and we have a single resistor, then the electron will move from the low potential. Technically, the low potential will be the negative terminal of the battery to the higher potential. Now, during its motion, the electron will the electric potential here of the electric field, the electric circuit system, it will decrease. And this is because of the resistor, because we know that the delta U is equal Q times delta V. Now, across the wires, there is no any change in the electric potential difference. So across the wire, conducting wire, it cannot be A and B. There is no any increasing or decreasing in the electrical energy. Since we are dealing here with electron, then the Q becomes minus E delta V. Now the minus sign means that the electric potential will decrease, and the correct answer will be D. If the ammeter in the circuit above reads 0, what is the resistance R? So here we have a wire connecting these junctions, and we have placed an ammeter to measure the current in this branch, and we found that the current is 0. What will be the resistance R? So this circuit is known as Wheatstone bridge, and this is a very efficient method that allows us to measure the unknown resistance here. Now, as you can see here, 3 ohm and the R are connected in parallel, as well as the 1 ohm and the 2 ohm, because we have this wire, although we have ammeter, but the ammeter is just a measurement device, so we can ignore the ammeter here, and we can say that the 2 ohm and the 1 ohm is connected in parallel with each other, because we have two terminals in common from this side and from that side. Now we can write that the delta V of the 1 ohm is equal to the delta V of the 2 ohm. Now the delta V across 1 ohm is given by, let's call the current here I1, and the current here is I2. So it's, according to Ohm's law, it's R times I. So R here is 1, and the I is I1. R here is 2, and the I is I2. So we can deduce that I1 is equal double I2. On the other hand side, the potential difference here is equal to the potential difference here. So delta V of the 3 ohm is equal to the delta V of the R. However, since there is no current through this branch, the same current I1 will be through, or will move through, the 3 ohm, and I2 will move through the R resistor. Now the delta V 3 ohm can be written as the 3 times I1, and for this one is R times I2. Now we have deduced a relationship between I1 and I2. So let's substitute I1 to be double I2. So 3, 2I2 equals RI2. Remember that we are interested in finding R. So let's move I2 to the other hand side. 3 times 2 is 6. 6I2 over I2 equals R. I2 with I2 cancelled out, and R is equal 6 ohm. This is a very repetitive question in AP exams, and the technique that we should follow is the same as this one. And let me resolve or reuse this technique in different questions. So for example, this question. In the circuit shown in the figure, the current in the ammeter is 0. So again, is 0. We need to know what is the resistance Rx. Notice that the 300 ohm and the 200 ohm are connected in parallel because they have two terminals in common. So this terminal and this terminal are in common. This terminal and this terminal are in common. As well as for the Rx and the 400 ohm, they are connected via two terminals. So they are connected in parallel. Now, since 300 and 200 are connected in parallel, they will have the same electric potential difference. So the delta V across the 300 ohm is equal to the delta V across the 200 ohm. Now, according to Ohm's law, this can be written as, let me assume that the current here is Ix and the current here is I. So also the current here will be Ix, and here it will be I, because the ammeter here is measuring 0 current. So no current will escape in this branch. Which means for the 300 ohm, the Ohm's law will be written as a 300 Ix equals 200 I. So we can say that Ix is equal 200 over 300 I, and the Ix is 2 over 3I. Keep this in mind. Now we jump into Rx and 400 ohm. We know that they are connected in parallel, so the 400 ohm voltage is equal to the voltage of the Rx. Now for the delta V 400 ohm, so 400 times I equals delta V Rx is Rx times Ix. Knowing that Ix is equal to 2 over 3I, 400I equals Rx multiplied by 2 over 3I. Now we just divide both sides over 2 over 3I, and we will get 400I over 2 over 3I equals Rx. Now I with I cancelled out. We keep change flip technique to calculate 400 over 2 over 3, or we can simply use the calculator to evaluate this result. 400 multiplied by 3 over 2, and this is the answer of Rx, and Rx is 600 ohm. The figure shows a circuit built from a battery and 4 resistors with the indicated resistances. The current in 2 of the resistors are also indicated. Which of the following claims correctly describes the directions and the magnitude of the current at point B? Now here we are assuming that there is a current carried by this wire, the wire that the point B it belongs to this wire. Now the thing is, we can say since this wire does not carry any electrical components, so one can say that R and the 4R are connected in parallel because they have the same 2 terminals in common. And also for the second 2 resistors on the bottom of the circuit, the 2 resistors are connected in parallel because they have 2 terminals in common. One terminal from the upper part and and the second terminal from the lower part. So we can say that delta VR is equal to the delta V 4R. So the potential difference here is equal to the potential difference here. And R times IR equals to 4R, the resistance times the current of 4R. Now R with R cancelled out, and we can deduce that the IR 4 of I 4R. So the current across or through this resistor is 4 times the current in this resistor, and this is obvious because the resistance here is less than the resistance here by 4, and according to Ohm's law, the current is inversely proportional with the resistance. If this increases by 4, then the current will decrease by 4. Now, due to the symmetry, and since we said also here, we have the same resistances as the previous one, but 4 are now on the left-hand side and R on the right-hand side. So we should say that the current here is equal to the I for I for R, and the current here will be exactly the same as here, which is equal to I R. Now notice that we have found a relationship between I4, IR and I4R, and we found that the IR is much greater than the I4R. So this current is not enough to feed this current. According to the junction law, the current that entering the junction should be equal to the current leaving the junction. So we must have here a current such that this current, in addition to this current, will make up the current through the R. The direction of the current is into the junction, so to the right-hand side, and the value of this current, it cannot be exceeded the I4, because I4, or IR, sorry, is equal to the I4R plus this missing current. So actually this missing current should be in a range between IR and I4R, which means the correct answer will be D. Toward the right, the direction is toward the right, and it's going to be in between IR and the I4R. 3 resistors are connected to an ideal battery with an EMF. As shown, 2 of the resistors have resistances of R0 and 2R0, as indicated in the diagram. The third resistor has a known resistance X. We don't know what is the resistance here. The current in the 2 of the branches is the indicated. So we know what is the current here and the current there. We don't know what is the current here, here, or here. we need to find the value of the resistance. To find the value of any resistance, we should know the delta V and the current through this resistor. Now, first of all, let's start with finding the delta V. Now, as you can see here, this X is connected with two terminals with the battery, as well as the R0 is directly related to the battery, so it's in parallel with the battery, and the 2R0, it's in parallel to the battery. So this complicated configuration tell us that XR0, 2R0, and the battery are connected in parallel because we have two terminals in common, which means the electromotive force or the electric potential difference or the electric potential drop across the 2R0, so the delta V across 2R0 equals to the delta V across R0 equals to the delta V across X, which is equal to the E. So we have found what is the electromotive or the electric potential difference across not only X, but also across R0 and the 2R0. Now it's time to find the current. We need to find the current across X. So let's start from I0. Now, as we can see here, at the junction point here, I0 will split it into two pieces. And since the resistance here is double the resistance there, then the current will be third its value here and 2 over 3 its value there. And we can prove it using the following. We know that the two resistors under the same electromotive force, so the delta V2R0 equals to the delta V of R0. Now, we don't know what is the current here or here, but we know that the I0 will be split into I1 and I2. So let's call this I1, and this one here is I2. Now, delta V2R0 is 2R0 multiplied by I1 equals R0 times I2, which means if we cancel R0 with R0, I2 is equal double I1. Now we substitute this in our equation, and we will get that I0 is equal I1 plus now I2 is equal to I1. So we just substitute instead of I2, we're going to write 2I1. Now I1 plus 2I1 is 3I1, which means I1 is equal, we divide over 3, 1 over 3 of I0. And this is what I deduced here. So whenever the current will be split across or into two pieces, one piece will go to 2R0, double the R0, and the second, the resistor is R0, always 1 over the third of the current will go to the higher resistance, and 2 over the third of the current will go to the less resistance. So now we know what is the current across R0 and 2R0. Let's focus on the current across R0. The current across R0 now is 2 over 3 of I0. Now the current through X will be toward the junction, this junction. Now let's call this current IX. We know that we have two currents will entering the junction to build up the 2I0. So the first current that entering the junction is IX. The second current is the IR0, which is the 2 over 3 I0. The combination of these two currents will give us the 2I0. My target is to find the current of IX in terms of I0, and then I use it to find the value of the resistance X. So IX is equal to I0 minus 2 over 3 I0. We just need to move the 2 over 3 I0 to the other hand side. And then IX is equal 2 minus 2 over 3 of I0. So the IX is equal 4 over 3 I0, and this is the IX. Now, we just can say that, remember that the delta VR0 is equal to the delta Vx So the delta V R0 is 2 over 3 I0 multiplied by R0 equals, this is the potential difference across the VR0. I know it's written as the E, but I need to write it in terms of I0 in order to find the expression, the correct expression of the resistance in terms of R0. Now it's equal to the delta Vx, and the delta Vx is the resistance times the current, and the current across or through the X is 4 over 3 I0. Now I0 with I0 cancelled out, 3 with 3 cancelled out, so 2 over 4, we divide both sides over 4 of R0 is equal X, so which means X is equal 1 over 2 R0, so X is equal R0 over 2. And the correct answer is B. Exercise 15, and will be the last exercise in this lesson. In the circuit shown, there are two identical batteries of EMF, two resistors of resistance R1 and R2, and the switch, which is initially open. The switch is then closed. What effect, if any, does closing the switch have on the potential difference across each resistor? So in the first trial, we have open circuit, so we can ignore this loop because it's open loop. We will consider only this loop by applying Kirchhoff loop rule. We can say that if we choose the direction of the current in this way and the direction of my loop in that way, so minus, so let's start with this point. So here I will start rotating in this direction, in the clockwise direction. Notice that the direction of my loop is opposite to the direction of the current. So the potential difference across R1 is the plus delta V R1. Now moving around the direction of my loop, we complete the rotation, it will be opposite to the direction of current, and the potential difference across the resistor should be positive. So plus delta VR2. And finally, we complete the looping to the battery. Since we are entering the positive terminal first, then the electromotive force should be written as a negative sign equals to 0, which means the electromotive force is equal. So if we move the electromotive force to the other hand side, it becomes a plus. So the electromotive force is equal delta VR1 plus delta VR2, which means the electromotive force of the battery will be divided, not necessary to be equal, between delta VR1 and delta VR2. So both electric potential differences for R1 and R2 is non-zero. Now, once we close the loop, then if we close the loop, this is the second trial, we can notice that we will be able to deal with three closed loop. This is the first closed loop, this is the second closed loop, and the third one is the larger circuit. However, to evaluate what will happen to the electric potential difference across R1 and R2, I will use this loop first, then to find what is the potential difference across R1, and then we use it to find what will happen to the potential difference across R2. So by applying the KLR, the Kirchhoff's loop rule, so let's use loop 1. We are entering first the negative terminal of the battery, so this is a plus E. We complete the circulation until we achieve the resistor. Now we're gonna choose an arbitrary direction of the current, and let's say that the current in this direction. Now, since the direction of my loop and the direction of the current is the same, then we use minus delta VR1. No need to write it in terms of Ohm's law because I'm trying to evaluate the delta VR, which is equal to 0. So the delta VR1 is equal to E. Now we're going to use this fact to evaluate the circuit in the right-hand side. Now let's consider the second loop. Now I will use the same direction of the current as before. So in this direction. Now the direction of the loop will be clockwise. Let's start from this point. Now, according to my direction, to the loop direction, not the current direction, here we're going to consider the loop direction. Since we are entering the positive terminal of the battery, this is minus E. Now we complete the circulation. The direction of my loop and the direction of the current are opposite, so we use the plus sign for the delta VR1, knowing that the delta VR1 is the E, so we just replace it by E. Now we complete the circulation for R2. Now again, we are rotating clockwise the direction of the current to the left. So this is a plus delta VR2 equals to 0. Now notice that we have minus E and the plus E, so they canceled out, and we can deduce that the delta VR2 is equal to 0, which means the potential difference across R1 has increased because in the previous trial, the E will be divided across delta VR1 and delta VR2 before we close the switch. So when the switch was opened, the electromotive force will be divided across this and this. Now all the electromotive force will go to the delta VR1, so it will increase. So not A, not B. And here, and for the delta VR2, previously when the circuit was, or the switch was opened, then the delta VR2 is non-zero. After we close the switch, it becomes 0. So what happened to the delta VR2 has decreased. So it will decrease. And the correct answer is D. And that's it for today's lesson on 11.6 and 11.7. Thank you for joining me. See you next time.